Section: Introduction. In this section, we discuss recent advancements in attention mechanisms that have allowed large language models to consider longer contexts. Earlier models like T5 and BART were limited to processing 512 or 1024 tokens, whereas newer models like Claude 3 or GEMINI 1.5 Pro can handle sequences of hundreds of thousands or even millions of tokens. Another approach called retrieval augmented generation, RAG, has emerged as an alternative to these long context models. RAG uses a two-step process where a retriever selects relevant context for a given query, reducing the burden on the generator to handle long contexts directly. While both RAG and long context models aim to address the challenge of answering queries from extensive text collections, there is a lack of direct comparison between them on a common task. Evaluating these systems poses a significant challenge. Some recent studies have introduced tasks like the needle in a haystack task, where models need to find specific information in a large document. However, these tasks may not be complex enough to differentiate between the capabilities of the latest large language models, as many models achieve near-perfect performance on them. In our work, we suggest using summarization as a way to evaluate long context models and RAG systems. Summarization requires understanding and condensing information from a lengthy context, which is crucial for assessing the effectiveness of these models. Previous evaluation methods for summarization have mainly focused on single document summaries or inputs of around 1,000 to 2,000 tokens. There is limited evaluation work on longer conversational or multi-document news summarization, typically restricted to about 10,000 tokens. One challenge in summarization evaluation is the reliance on low-quality reference summaries and automatic metrics that may not align well with human judgments. To address these limitations, we propose using synthetic data generation. We create a large corpus of documents, the Haystack, on a specific topic, ensuring that key information repeats across documents. This setup allows us to automatically identify relevant insights for a given query. Systems participating in the summary of a Haystack, SummHay, task must summarize these insights and cite the source documents accurately. Our contributions include a method for generating haystacks in conversation and news domains, a detailed pipeline for task feasibility and validity, and an evaluation protocol focusing on coverage of reference insights and citation quality. We conducted experiments with LLM-based evaluation and found promising results. Our study also includes an estimate of human performance on SummHay and a comprehensive evaluation of RAG systems and long-context LLMs. Our findings highlight the challenges faced by these systems, the trade-offs between RAG and LLM approaches, and the impact of advanced RAG components on task performance. We have made our dataset and evaluation methodology open source, aiming to advance the development of more reliable and effective answer engines in the future. Section Summary. In this section, we introduce recent advancements in attention mechanisms that have enabled large language models to process sequences of hundreds of thousands or millions of tokens, surpassing previous limitations. We propose using the task of summarization as a means to evaluate long context models and retrieval augmented generation, RAG, systems, addressing challenges in evaluating these systems due to the lack of high-quality reference summaries and reliable automatic metrics. Our work focuses on generating synthetic data for the SummHay task, evaluating system outputs based on coverage of reference insights and citation quality, and comparing the performance of RAG systems and long-context LLMs on this challenging task. Section: Related work. In this section, we will discuss the existing work related to summarization evaluation. Previous studies have mainly concentrated on evaluating the relevance and coverage of summaries, especially in scenarios with short inputs and single documents. Recent research has expanded this evaluation to include longer inputs. Some studies have focused on assessing coherence and faithfulness in book summarization across different domains. For coverage evaluation, researchers have explored content selection methods, two-step extract evaluate frameworks, and the correlation of various metrics in coverage assessment. We use summarization relevance as a basis for evaluating long context scenarios. Our approach involves creating synthetic data and simplifying the relevance evaluation process to generate a highly correlated automatic metric. To evaluate the long context recall ability of language model models, LLMs, the needle in a haystack method was introduced. Subsequent studies have investigated factors like needle placement, multi-needle variations, and multimodal variations. Various benchmarks for long context evaluation have been developed by enhancing existing tasks and datasets, addressing context length extension, and dealing with data contamination issues. Moreover, several studies have introduced synthetic data to complement existing tasks, making it more challenging for current models. Our benchmark focuses on synthetic data with around 100K input tokens, emphasizing tasks that require aggregation and complex reasoning over long contexts. In terms of attribution evaluation, benchmarks have emerged to assess LLMs' ability to ground their generated content with citations. Our study specifically examines attribution in the context of long input summarization, enabling us to trace insights back to their sources and evaluate summary citations directly. The SummHay framework involves the synthesis of Haystack data, where LLMs respond to queries by generating long-form answers that involve identifying and summarizing recurring insights across documents while citing the source documents. The Haystack generation process includes subtopic and insight generation, where subtopics are expanded into specific insights that are unique and relevant to a single subtopic. Documents in the Haystack are generated one at a time, incorporating a set of insights across subtopics to ensure realistic and unique content. The evaluation of the SummHay task relies on precise mapping between insights and documents, with multiple verification processes in place to ensure the quality of the generated haystacks. Section Summary. In this section, we explore existing work on summarization evaluation, focusing on relevance and coverage assessment in both short and long context settings. We delve into the long context LLM evaluation, discussing the needle in a haystack approach to evaluate LLM's recall ability in long contexts and the creation of long context evaluation benchmarks. Additionally, we investigate attribution evaluation, studying LLM's ability to ground their generation with citations, particularly in the context of long input summarization, utilizing synthetically generated data to trace reference insights to their sources for direct evaluation. Section. Haystack Summarization, Figure 1, Right. In this section, we have created haystacks according to a specific method. These haystacks are then used for a task called Summary of a Haystack. We use a language model to turn each subtopic into a question, like, what do students talk about when it comes to managing stress? Each system working on this task must make a summary in bullet points to answer the question about a single subtopic. We tell the language model how many bullet points the summary should have, which matches the number of insights in the subtopic. This helps us control the length of the summaries, which is important for evaluating summarization. We show in a section that this choice effectively controls the length of the summaries. The system is also told to mention the source documents in each bullet point using a specific format, like 1, 2, with document identifiers from the haystack. This bullet point structure and citation format are crucial for our evaluation, as explained in a section called SummHay Benchmark. We apply this method to two areas, conversations and news, which are common for summarization testing. For each area, we create 5 haystacks, with an average length of 93K tokens. Each haystack has around 9.20 subtopics, each with about 6.75 insights, totaling 62 insights per topic. In the news domain, we use documents as the starting context. We use a mix of GPT 3.5 and GPT 4o for the language model and provide more details in the appendix. We first define task metrics, ensure that manual annotation can be reproduced, and then evaluate the quality of automated evaluation. One metric is coverage, where we check how well a summary covers the insights of a subtopic. Another metric is citation, where we compare the citations in a summary to a set of correct citations for each insight. The joint metric combines coverage and citation to see if a summary covers the insights and cites the documents correctly. We calculate scores for each metric to evaluate the summaries. To make sure our evaluation process is consistent, 2 authors and 2 annotators independently reviewed a set of summaries and assessed the coverage of insights. The results show a strong agreement between the annotators on which insights are covered by a summary and which bullet points cover each insight. Annotating one summary takes about 4 minutes on average. To make evaluations more efficient, we explore using language models for evaluation instead of manual annotation. Section Summary. In this section, we utilize the Haystack summarization method to create haystacks and then apply them to the summary of a haystack task. By transforming subtopics into queries and instructing the LLM to generate bullet point summaries with specific citation formats, we control the length of the summaries for evaluation. The evaluation protocol includes metrics like coverage, citation, and joint scores to assess the quality of automated evaluation, ensuring that the generated summaries cover insights and cite documents accurately. Section: Automatic Metric Validation. In this section, we engage 2 professional annotators to mark 200 potential summaries, split evenly between news and conversational topics, alongside reference insights. The annotators were paid $25 per hour, and the task took a total of 13 hours, costing $325 in total. We provided a task prompt with instructions and an example summary containing fully covered, partially covered, and uncovered insights. We assessed the performance of 5 language models, LLMs, GPT 3.5, Claude 3 Haiku, Opus, GPT-4o, and GEMINI 1.5 Pro, based on their correlation with human annotations, linking accuracy, and evaluation cost. Our analysis revealed that GPT-4o and GEMINI 1.5 Pro showed a strong positive correlation, 0.7 plus, with human annotations. We opted for the GPT-4o model as our evaluator due to its high correlation at a lower cost compared to GEMINI 1.5 Pro. We experimented with providing 9 few-shot examples in the prompt, denoted as GPT-4o 9FS, which led to minor correlation improvements but at a higher cost. Therefore, we settled on using the original prompt and the GPT-4o evaluator for auto-evaluation. We also investigated potential biases in automatic evaluation using GPT-4o, focusing on favoritism towards specific model families or summary lengths. Our analysis in the appendix showed no evidence of systematic bias in the LLM-based evaluation under our protocol. Moving on to the experimental settings, we evaluated both long-context LLMs that access the full Haystack and Retrieval Augmented Generation (RAG) systems, where a retriever filters relevant documents for the generator. We tested various recent LLMs with context lengths exceeding that of an individual haystack, including models like Command R, GEMINI 1.5 Pro, GPT-4 Turbo, and Claude 3. Additionally, we assessed RAG systems with different retrievers, such as KWs, Vect, Sentence Transformers, and Lange, along with baseline models like RAND and ORIC. Our benchmark results summarize the performance of 10 summarizers across long context and RAG settings in terms of coverage scores, citation scores, and joint scores. We observed that the choice of retriever significantly impacted coverage scores, with top-performing LLMs achieving strong coverage even without retrieval. Citation scores improved with better retrieval, emphasizing the importance of optimizing retrieval for citation quality. Gemini 1.5 Pro stood out for achieving comparable citation scores in both RAG and long context settings. Considering coverage and citation, the joint score provided a comprehensive evaluation of system performance on SummHay. While all summarizers performed best with the Oracle Retriever, the RR3 Retriever in the RAG setting yielded the best realistic performance for most models. We identified areas for improvement, such as RAG systems underperforming compared to the Oracle setting and models struggling in the full context setting. In conclusion, the performance of different models varied based on coverage and citation trade-offs, highlighting the potential for further advancements in RAG systems. The average bullet point length varied among systems, with some models closely matching human-written bullet points. Our analysis in the appendix further explored the breakdown of citation scores into precision and recall, revealing trade-offs in system performance metrics. Section Summary. In this section, we conducted automatic metric validation by recruiting 2 annotators to assess 200 candidate summaries in news and conversational domains. We evaluated various LLMs for insight-level coverage and linking accuracy, ultimately selecting GPT-4o as the evaluator due to its high correlation with human annotations and cost-effectiveness. Additionally, we explored long-context LLMs and RAG systems for summarization, finding that the choice of retriever significantly impacts coverage and citation scores, with GEMINI 1.5 Pro standing out for achieving comparable citation scores in both RAG and long-context settings. Section: Estimating human performance. In this section, we estimated human performance by having 2 annotators complete the task. We set up the annotation environment and then analyzed the outcomes. The annotators worked in the Oracle setting, where they only saw relevant documents for the query they were summarizing, reducing the amount of text they had to read significantly. This likely sped up the annotation process, although we couldn't confirm by how much due to practical constraints. The 2 annotators created a total of 10 summaries, 5 each for conversational and news subtopics. While this is a small sample compared to the full benchmark, we believe it gives a fair idea of human performance. The results showed that participants improved steadily during the sessions, with both coverage and citation metrics increasing quickly in the first 90 minutes and then more slowly in the last 30 minutes. The citation score is similar to the F1 measure, and we also looked at precision and recall of the citations. Precision stayed around 80.0 throughout, while recall improved steadily. Comparing human annotator scores with LLMs and RAG systems, humans performed significantly better on the SummHay task. We caution against seeing human performance as the upper limit, as with more time and clearer instructions, annotators could do even better. Our aim is for human performance to serve as a reference point for what can be achieved on the benchmark, expecting future systems to match or exceed human performance. Additional details on guidelines, recruitment, and task framing can be found in the appendix. Section Summary. In this section, we estimate human performance by engaging 2 annotators in the task, where they work in the Oracle setting to summarize documents related to specific queries. The results show that human annotators outperform LLMs and RAG systems significantly on the SummHay task, with a joint score of 56.1 compared to the best system performance of 44.6. We caution that our estimate of human performance is not an upper bound, and we anticipate future systems to match or exceed human performance levels on this task. Section: Reliance on automated evaluation. In this section, we did not find any significant bias towards a specific group of models. However, our results indicate that there is room for improvement in both coverage and linking evaluation. Gemini 1.5 Pro, although more expensive than GPT-40, had a rate limit that restricted its use in our study. We did not test cost-effective non-LLM-based NLI and relevance metrics, which showed poorer performance with smaller NLI models for identifying unrelated sentences in long-form question-answering tasks. The generation models we studied are all closed-source models. While these closed-source models generally perform better than open-sourced models, this performance comparison can vary depending on the task. We did not include high-performing open-sourced models like Llama 3 because they cannot handle the minimum 16K context window needed for our RAG experiments. By allowing up to 15K tokens in the RAG setting, we achieved an Oracle Citation F1 score of 0.84 across insights. This balance between reducing input size and task feasibility is crucial. We suggest exploring RAG systems with different input lengths and models designed for output citation in future research. We also encourage testing longer context, open-sourced models on SummHay for benchmarking purposes.